talks are online.
Yeah, but at least you got the chance to get so many good speakers, yeah?
Yes, yeah. That's nice, and including you. So we are very lucky that you agreed to talk here online. And last time also in 2018, we had something in Calcutta. There we also spoke online. So maybe,
correct, yes.
yeah, maybe next we should see when the situation is improved to have you here in person at some point. So, maybe you can, I don't know, the organizers are there, so we can start formally, is it?
I think we should wait for a few more minutes before the participants join. I think our average participants are being like 50.
Okay.
So,
okay, yeah. Maybe we can wait. In the meanwhile, Gerardo, if you don't mind, you can start sharing your slides or something.
yeah, let's just test the sharing if it works or not.
Okay, now you gave me permission. Very good, thanks.
Yeah, it works. Can you move around a few slides? Sure.
Good.
Yeah, so. Yeah, so it's three. I will ask Professor Majumdar to formally introduce Professor Adesso and then start the session.
Okay, so let's start this session formally, and I'm very pleased to welcome Professor Gerardo Adesso, who is a professor of mathematical physics and director of research, Faculty of Science, School of Mathematical Sciences, University of Nottingham, UK. And I've had the great pleasure of knowing Gerardo for many, many years, and we have met in the various meetings at several places around the world. And of course, he's very well known, so he doesn't really need an introduction, but for the benefit of young students, young people who are here, his research interests actually span the field of quantum information, entanglement theory, quantum correlations, quantum foundations, quantum optics, quantum metrology, quantum technologies, condensed matter physics, and many-body physics. And he's mainly interested in identification and quantification of information technology. His goal is to understand the most essential signatures of quantumness in elementary and complex systems, so as to cast light on foundational aspects of quantum theory, and in the process also devising novel ways to exploit quantumness for operationally and in robust applications. So Gerardo is very well known for his many, many interesting and significant works, which all young students are welcome. In fact, they are invited to look into. And today he's going to speak. The title is Every Quantum Helps. So without further ado, Gerardo, please, you can start your lecture.
Oh, thank you very much. Thanks. Yeah, that was a very nice introduction. Actually, you gave a bit of my talk already, because yeah, I was about to say what we care about. So for many years in Nottingham, then I would think of myself as someone patrolling the border between the classical and the quantum world. And this border is not very well defined, right? So this is a very nice illustration by Zurek. And the thing is, we know some things which are obviously quantum, and once we see them, then obviously we say there's no way we can match this description with just classical probabilistic statistics theory, for instance, Bell non-locality, like it was recognized by the Nobel Prize last year. But then there are some more subtler effects where it's unclear to what extent we recognize a signature of quantumness, or to what extent we see a deviation from classical behavior, and what we can do with it. So the main goal of my research, as you said, is to characterize this border from 2 points of view. One is more fundamental, because the more signatures, the more traits of quantum mechanics we are able to recognize and rigorously characterize and quantify, then the best we understand the structure and the nature of quantum theory itself. in systems of increasing complexity, which might still exhibit some quantum behavior, despite being in what traditionally you might think of the classical domain. But the other hand is the more practical perspective, where we know that some quantum features are useful for information processing. So the more we understand, the more we characterize, the more we give an operational interpretation to, then perhaps the best we can perform certain tasks in computing, communication, and so on. Right, so the idea more generally is what makes quantum technologies tick. So what gives them the advantage? What are the ingredients? They really rely on something quantum. But does every quantum thing provide some advantage? Well, the other day I was shopping in a supermarket in my city, and then I found this quantum deodorant, and who knows? I mean, is this better than the classical one? I don't know. There's so many things these days with quantum in the title, it became a little bit of a hype. So we want to get some firm answers to what really quantum features actually help for quantum information processing and what are just hype and irrelevant things. So we know one which definitely works. That is the most famous resource we know. It's entanglement, and you can find, I don't have to define entanglement in this workshop, you can find representations of it all over the place. Clearly in mathematical terms, it's very well defined as being non-separability of quantum states. You can find very nice artistic expressions for entanglement as well. This one on the left, I own this picture. It was gifted to me by an artist in the US. I'm very proud of this. But what I care about is the fact that entanglement is helpful, but actually every little entanglement helps, in the sense that there are a few papers over the years which have shown very specific results, saying there exist tasks such that any entangled state, even bound entangled or even just slightly outside the space of separable states, provides an advantage in the performance of those tasks. These tasks can be related to assisted teleportation, can be related to channel discrimination, and so on. So this means entanglement, in a clear mathematical sense, is a resource for quantum technology. So the idea is, what other resources we can characterize, what is useful, and what constitutes an ingredient which allows us to get better than any conventional classical technology. This brings us to the formalism of resource theories. And it's nice to explain this with a little bit of a metaphor. Suppose that you, I don't know, you inherit some shed full of stuff from your distant relative, and you don't know anything about that. And this contains lots of machinery that you just get for free. Okay? This will be a metaphor for free operations. On the other hand, you want to experiment with these things, and then what you do, you start supplying some inputs to this machinery and see what happens. And then you realize there are lots of inputs which don't get you any useful effect, but there are specific things that you can input into this free machinery, and then you get something useful out of it. So in this cartoon, the empty bottle would be like a free state. This junk that you don't know anything about would be your free operations. And this red substance in the bottle would be a resource, which once combined with these free operations allows you to do some useful effect. In this case, switch on a lamp. This is an analogy. Of course, we have more mathematical characterization of this. And there are many phenomena that you can characterize as in terms of resource theories. For resource theories of states, what you can do, you can divide your set of quantum states into a subset that you consider free states, the ones that do not contain any resource. For entanglement theory, this would be separable states. And then any other state outside would be a resource state, like an entangled state or a maximal entangled state. And similarly, you can characterize the operations as free operations, which are the ones who are not able to produce any resource from free states, like local operations and classical communications for entanglement. Any other operation requires the consumption of some resource. So it's related to, it's restricted. You cannot implement it for free. And in entanglement theory, this is clear because the paradigm is having distant observers who can just locally control their systems and communicate classically. Anything else beyond that, say you have an entangling gate, a control not gate, this will come at a cost. In this way, you can process and manipulate your states. If you start from free states and you act on free operations, then you will just get another free state. If you start from a resource with free operations, you might get still a resourceful state, but its resource content should not increase. So this gives a criterion to validate any quantifier of your resource, like entanglement measures are monotonically non-increasing under LOCC. And in some cases, you can decrease this resource content to some extent up to the fact in which you destroy it completely, so your state becomes free. On the other hand, if you start from a free state, by means of non-free operations, you can create some resource, and then you can use it for further processing. So once you have this framework in place, there's lots of questions we can ask and answer, like under which conditions you can convert states into each other just by using free operations. That's manipulation, resource manipulation. And then you can ask, for instance, what is the most resourceful state that I have in my theory? This would be the one from which, just by free operations, you can go and create any other state, and maybe from which you can distill. This can be helpful to create more copies, and you can distill this back to its purest form. So you can look at the rates of creation and distillation. You can look at many different things. What is not automatically included in this framework is, what is my resource useful for? So once I quantify something and I know that my state is non-free, that number, what does it mean? So is it a resource for what? That's what we want to answer today. So I'll give you two examples. One approach is more indirect. The other one is more direct and holds for every quantum resource theory. The indirect one starts from the fact that we know that entanglement is a resource because there are some general results that I showed about it. So we can take some other resource and just convert it to entanglement by means of operations which are free for the original resource. And then we will use entanglement for whatever we like. So this means the original thing is a resource because it will allow for creation of entanglement, which is then a direct resource for some protocol. So how does this work? In order to explain this, I will focus on a case study, which is perhaps the most fundamental resource we have in quantum mechanics, which is superposition in a basis. Quantum coherence plays a very important role in various phenomena, including the structure of quantum correlations, potentially some of biological function. It definitely is an ingredient important for metrology and sensing, and it's been widely studied for its effects in condensed matter, many body physics, and thermodynamics as well. So how does the resource theory of coherence works? Well, very simply, you need a basis. And this basis can come from the physics of the problem, right? But for every resource theory of coherence, it's defined with respect to a basis. Once you have specified the basis, then the incoherent states are those with a density matrix that is diagonal in that basis. While any state with some of diagonal element would be a state with a resource, so a coherent state, resourceful one. So the incoherent ones are fully invariant under complete defacing in the reference phases. On the other hand, the free operations, then these will be operations that do not create coherence. Let us visualize something, for instance, for a qubit. For a qubit on the block sphere, if we pick the computational basis, then all the incoherent states are along this vertical axis, the z-axis, while any state which is outside the axis on the ball, that will have some coherence, and the state with maximal coherence will be on the equator, according to all possible measures that you can think of, which are valid in the resource theory of coherence. While talking about operations, there's so many different classes that people have proposed, and I do not have time to go into the details here. You might pick the one you like, but luckily the results I'm going to present, they involve some quantifiers, which is monotonic among all possible classes of operations. So we don't need to enter the debate of choosing which class is more physically significant. But you can check the review if you like it to see what was the status. Actually, it's getting old already, right? It's 5 years ago. So maybe there are more modern developments which include even more classes in this. So once we have this, what did we do? I promised some indirect interpretation. The indirect interpretation is coherence is helpful because it allows for creation of entanglement by incoherent operations. And it works this way. For those of you who are familiar with quantum optics, this is very inspired to the conversion of optical non-classicality to entanglement by means of passive operations like beam splitters. So in this result, which we obtained with some colleagues in India, actually, when I was visiting HRI in Allahabad, the scheme is as follows. We have a system of interest, and we have an ancilla which is prepared in an incoherent state. And we are allowed to do only incoherent operations between system and ancilla. If we do so, and the system is also incoherent, then of course the output will be incoherent as well. Let me see if I can use this pointer thing. You see it, right? I hope, in the Zoom. Yeah, so the output is also being coherent, but it's actually separable as well. So you can't create entanglement this way. On the other hand, if your input has coherence, the ancilla no is still incoherent. The operations are still incoherent. So just the ingredient you supply is coherence in your system input. Then you can create entanglement in this way. And actually, this is an if and only if. So the state of your system is coherent if and only if entanglement can be created from it with an incoherent ancilla by means of incoherent operations. So there's a one-to-one correspondence between coherence and in input and entanglement in the output. And back when we did this work, then this was also made quantitative, because back in that time, we didn't really know much about coherence theory. We didn't know many measures for it, but entanglement theory was more developed. So we exploited this correspondence in order to construct quantifiers of coherence defined in terms of the maximum entanglement in the output that you can obtain by incoherent operations on your system and an incoherent ancilla. And that was quite successful. So I think in the end, many other papers have now studied conversion of resources in this way, always typically leading to entanglement in the end, because that is the most well-studied and the ones we understand the most as useful for some information processing tasks. But it's still an indirect thing. Clearly, coherence is useful for this, but we want to understand if it's useful in a more direct fashion. So how do we do it? We consider a case of channel discrimination. Right, so what do we do with it? Before I introduce the protocol, let me just focus on one quantifier. There's so many ways of quantifying resources. I will focus on one which actually plays a role in the protocol I'm about to explain. This is called robustness. It was defined for entanglement before. It has been studied for many other resources. For coherence, it is quite simple. And the idea is this geometric picture here. So you have your quantum space of quantum states. There's the subset of free states, in this case, incoherent states. And then the idea is you take your state rho, and you want to mix it with some other arbitrary state tau, and look at the weight of the mixture, which is this real number S. And then you're looking for the minimum value of S, such that this normalized mixture loses all its coherence and becomes incoherent. So ends up being in state delta, which is inside the free set. So robustness is the minimum weight of mixtures of your state with another state, such that all of its coherence is destroyed by the mixing. That's why it quantifies how robust your state is against being mixed with something else. And yeah, it can be computed if you like, can be expressed as a semi-definite programming for coherence, and it has some nice interpretation that is related to witnesses that separate your state from the space of incoherent state. So it's a nice quantifier. It behaves well, and it's monotonic in all possible resource theories of coherence. Right, keep this in mind, and let's look at the protocol now. So this is a protocol in which you want to guess what happens inside the black box. So you prepare an input state, and then you send it through the box. In this box, the state might be shifted by some unitary. This unitary is just generated by a Hamiltonian that is diagonal in a given basis. So clearly the problem is telling us that we should consider the role of coherence with respect to this basis, which is the eigenbasis of the Hamiltonian. So the system will always be shifted around the axis specified by this basis, but we don't know by which angle it will be shifted. Actually, what we know is that there are a few possibilities, say phi 1, phi 2, phi 3, each of those with some prior probability. This one is known to the experimenter before the protocol. But then it goes in, then just one of these instances is chosen. So it's a discrete set of possibilities. Then the state comes out. And then what you want to do, you want to measure and guess what instances happen. So you need to come up with best P of M, and then you have to, from there, guess the value of K, which corresponds to the shift that happened inside the black box. What is the figure of merit here? The figure of merit would be the probability of guessing correctly that you calculate this way. So you optimize over the output P of M's, what? The expectation value of the corresponding POVM element calculated on the output state after the shift, weighted by the prior probability of that instance. That's the quantity we want to maximize and will tell us how useful our input state is for the protocol of, in this case, phase discrimination. Right, so one consideration is if we start with the state which is incoherent with respect to the generator of this transformation, then it's totally useless because it's invariant under the unitary. It's as if you want to estimate rotations around the z-axis and you come with a vertical stick, perfectly isotropic, not like this pen, whichever way you rotate, it will just remain the same. So you don't see anything. So if you use an incoherent state, the best you can do, because the state comes out unchanged, to guess the k, you just put your money on the instance which has the highest prior probability. So it's just the maximum of all those pk's, which is your probability of success. On the other hand, if you have states with coherence, say they are a bit tilted, then they will be affected by this unitary. So you have a chance of guessing better with the proper measurement what happens at the end. And so you can calculate this for any input state in any dimension. Actually, we did this. And then what you find is the following. The probability of guessing correctly with an input state that is not free would be larger than the probability of guessing correct with a free incoherent state. And so the ratio between these two quantities is larger than 1. But by how much is larger than 1, it's exactly quantified by the robustness of coherence in the initial state. So there exists, for any state which is non-free, there will exist some setting of this phase discrimination game, specified by some prior probabilities and some sets of values, such that the robustness of coherence quantifies exactly how much advantage your state allows you to achieve in this protocol compared to using any free state. So coherence is a resource, both qualitatively and quantitatively, for the problem of, in this case, phase discrimination, and the amount of coherence tells you how useful your state is for this compared to not having coherence at all. Okay, so it's a qualitative and quantitative result of direct relevance that confirms the resource role of coherence in a specific case, right? In the family of channel discrimination protocols. So this was a paper which we really liked to do a few years ago, and we did experiments as well. We generalized to multi-level coherence, and there were other results for other resources as well. These are just some of those which were available at the time. Then people have generalized these even beyond quantum theory. And it seems that there's a trend in studying robustness of resources and discrimination problems and seeing that the advantages are quantified by this measure. And there's a very nice geometric root behind it. So we thought maybe this is not just something specific to coherence, it actually might hold for more general resource theories as well. And the answer is yes, that is true. So I will give you now the results. They're very similar to what I've shown so far, but I will explain the setting in more generality. And the only hypothesis I have at the moment is my resource theory is convex, which means the set of free states is convex and closed. This includes entanglement, coherence, magic state distillation, many other resources in quantum information, but not all of them. Yeah, so if you mix any free state, they will remain free. Right, so we don't need to specify what is the physical resource. We just say we take the space of quantum states, identify this, it's like an egg yolk here, as a set of free states, and then we want to see if anything outside this set is useful for something. And the something is again a channel discrimination problem. Now we don't have the intuition anymore what is the nature of these channels. Before it was some nice phase shift. Here they can be generic channels. But the idea is state enters the black box. Here a set of sub-channels might happen, which are just completely positive trace non-increasing maps, which will adapt to an actual quantum channel trace preserving map. And then we need to measure at the output, and then we need to guess which particular sub-channel has been applied to my state. So again, the probability of guessing correctly is given as before, depending on the state, on the set of sub-channels and the measurements that I get through this weighted average here. I don't have to have the prior probabilities. They are embedded in the subchannels. If you like, this will include just channel discrimination. Each subchannel you can explicitly model as a quantum channel times the probability, which makes it trace non-increasing rather than trace precisely. So it will incorporate the previous case as well. And then this is just enough. So once we have this, then we just look at witnesses which separate my state from the set of free states, assume convex, and then we can replicate the previous results. So for any convex resource theory, every state which is non-free is useful for some subchannel discrimination task. Mathematically speaking, it means every state which is outside the free set, for every such state, there exists some subchannel discrimination problem such that my state has a better probability of success compared to any free state. So look at this. For every state, we will find a problem that makes that state useful. Yeah, so this is not a universal problem. It depends on the state. And I can quickly go through the proof if you like. Actually, one direction is trivial because the set is closed. So if you find something outside, something larger, you must be outside. But the other direction, we can do it constructively. So for every state outside the set, I can construct a very simple binary discrimination problem, just two channels. And I can show that for these two channels, discrimination works better with my state compared to any free state. And these channels, as I was hinting, they're constructed by exploiting the connection of witnesses. So witness operators, we can have let's say, a complement to witness operator, which is an observable X that has bounded trace for any free state between 0 and 1, so bounded expectation value, but its expectation value on any state outside is larger than 1. Yeah, and then it's just projections onto qubits involving expectation values of these operators, which are my two channels that I'm aiming to discriminate. And for binary discrimination, we know how to calculate probability of success because it's just a Hellstrom measurement that we have to do. So it depends on the trace distance between them. I don't have to go through all these details, but we can compute them. And then based on the constructive properties of this witness, then you can show that it is larger than 1, this ratio, if and only if you are outside the set. So there's always a pair of channels which I can distinguish better by not being within the convex set of free states. And then the next question would be, yes, but how much advantage do I gain by actually not being free? How much better I can discriminate those channels? And you can guess the answer. What is it? The answer will be given once again by the robustness. So I can define the robustness for any convex resource by just considering again the minimum weight of mixture until I lose my resource and I end up on the set of free states. It's the same definition, just the F is more general. And I don't have to tell you which one it is, just convex at this stage. This can be recast as a convex optimization problem due to the properties of that witness operator. It's not always a semi-definite programming. Yeah, sometimes it may not be. Say for entanglement theory, this is not a simple semi-definite programming problem because the set of separable states is hard to characterize. So the separability problem is NP. We can't just cheat our way out of this, but it will still be expressible as a convex optimization problem. And then the answer is as before. For any state which is outside my free set, the maximum advantage that my state enables in channel discrimination compared to any free state is given by the robustness of the corresponding resource of my state. And again, I can prove it, but I don't think I want to do that because I will rather just go to some of the more general results I have later. But it just one direction follows from the definition of robustness in the optimal pseudo mixture, where we find the optimal sigma and tau which realize this decomposition. And you can do it by simple linearity and discarding a term. The other direction has to be constructive again, and follows from the recast of the formula for robustness in terms of convex optimization. And we use a little bit of convex theory of duality there. And then we have to construct a set of channels for which we can show that this advantage is larger or equal than 1 plus the robustness. And this is done. It's written somewhere in the paper. I don't have to go through all these steps here. It's going to be boring, but it's not that difficult. Right, so what we have found so far was that for every convex resource theory, robustness quantifies the advantage in channel discrimination. And we were focusing on resource theories of states and looking at discrimination of channels, but there's a nice duality between these and other approaches to resource theories. For instance, you can consider dynamical resource theories, which are resource theories of channels, and then you would consider super channels as operations, or you can consider resource theories of measurements, and then you look at the advantages in state discrimination. All of these things are connected. There were a few papers all at the same time when we published ours just before the pandemic, and then they always established this kind of multi-valued approach between a robustness measure, some discrimination problem, and an information theoretic quantity related to the geometry of the problem. And I think one of the most general ones was by my former collaborators and student, Bartosz Regula, and visiting student Ryuji Takagi, where they incorporate all of these results and even generalize to general probabilistic theories beyond quantum theory. That was in the context of channel discrimination. Another approach, which is very similar, is instead of guessing the instance between a discrete set of options, we want to actually estimate some unknown parameter which has been imprinted on our quantum state. This is, roughly speaking, the general premise of quantum metrology, which exploits all sorts of quantum features in the input, in the measurements, in the state, to improve the available precision in estimating physical parameters which might not be directly observable, like time or phase. So the typical approach in quantum metrology is you have an input state, it goes through some black box. This black box will encode some parameter on your state or multiple parameters. And then you have to come with an optimal measurement, and from it you will reconstruct the statistics for the unknown parameter, which takes the form of an estimator, a probability distribution, if you like. For unbiased estimators, your probability distribution will be centered in the true value, but what distinguishes a good estimator from a bad one will be the variance. Yeah. So you want the estimator with the smallest variance, which will characterize a higher precision, so smaller error in your guess. You can repeat this many times in order to further narrow the statistics by statistical factor. And what is known in a nutshell is that the quantum Kramer-Rao bound tells us there is some fundamental limit to the precision of estimating an unknown parameter. And this means that the variance for any possible estimator of your parameter is bounded, lower bounded by, apart from the statistical factor, by 1 over the quantum Fisher information, which is a nice quantity that you can calculate geometrically starting from the fidelity of the quantum state when you do an infinitesimal variation of the parameter. But it's a nice object with lots of interesting properties. And for our purposes, because this bound can be saturated for a single parameter, it means that you are looking to find the strategies which maximize this quantum Fisher information, because this will guarantee the minimization of the corresponding estimation error. So if you want to see how useful your state is compared to any state in a different set, you might consider a metrological advantage as the difference between quantum Fisher information for a given metrological problem, using your state as input, minus the maximum quantum Fisher information using any free state. Now, for entanglement theory, it was well known that entanglement is a resource for metrology, but also coherence is a resource for metrology, because if you need to estimate a parameter generated by a certain Hamiltonian, you would need coherence with respect to the eigenbasis of that Hamiltonian, for the same reason as I've said in the beginning with the discrimination problem. Otherwise, your state doesn't pick up any information about the phase. So there are already many instances of useful resources for metrology, but again, we can look at quantifying the advantage more generally in terms of just taking a convex resource theory and comparing Fisher information for a state which is outside and for all states which are inside the set of free states. In this case, instead of the ratio, you can just take the difference of quantum Fisher information. So what happened? We had a paper looking at the resource theory of identical particles, entanglement, which has been a hotly debated topic. And we came up with a way of formulating it at particle level and validating proposals for unlocking this resource into mode entanglement, like it was proposed by Martin Planey and collaborators. And we understood that this is a similar instance to this indirect approach, which converts coherence into entanglement. So we have a consistent resource theory for identical particle entanglement. And in there, we were able to actually give a rigorous proof of the fact that identical particle entanglement is a resource for metrology by constructing a quantifier that was effectively based on this, okay, where the free states in that case, they would be the particle separable states. And then we could prove that this quantifier, based on quantum Fisher information, is a valid monotone in the resource theory that we had constructed. So this was one instance in which we quantified advantage and showed that it is a valid monotone in a consistent resource theory. As about the same time or soon later, there was a more general paper, again by my former student Bartosz. And that paper is, if you want, the analog of the previous theorem that I have shown before. So we had a general theorem in channel discrimination, which is a discrete guessing game. And now we have a general theorem in parameter estimation, which is a continuous guessing game. And it says the same as before. In any convex resource theory, for any state outside the set of free states, there always exists some parameter estimation problem with some channel and measurement, such that the advantage defined in terms of difference of quantum Fisher information is strictly positive. So your state will be more useful than any free state at some parameter estimation problem. If I pick another state, then there will be a different problem for which that state is the most useful for. Yeah, I hope this is clear. So if we want to summarize these two lines of results so far, and before I move to the last part, we have a discrete approach in channel discrimination problem. We have a continuous approach in parameter estimation problems. Both of these are kind of metrological sensing schemes. Both of these involve having a probe, having an optimal measurement, and trying to guess or precisely reconstruct what's happening in the black box. In both of these cases, whichever is our structure of states, as long as we identify a free set of useless states that is convex, then anything outside is a resource. Because for any state, we can find one of problems of this kind, such that my state does better than any free state. It's a little bit convoluted, I would say. It's not what you normally would think of. Say, I have a problem, and then I need to find my resource. This is, I have a state, and then I will find a problem which makes my state look useful. So somehow, when I like these results because they're general and mathematically very nice, but physically speaking, they're a little bit odd, right? So it says, it's a bit like this quote that sometimes is misattributed to Einstein. I don't know where this quote is from, but they say, let's say every state is useful, yeah? Every quantum helps, as my title says. But if you just pick some problem for which your state isn't fit for purpose, then it will do very badly. But all of these results, they are in the best case scenario. And we are able to show that there exists a best case scenario such that every state which is not considered free would give you a noticeable advantage in discrimination or estimation problems. This is the results we have gotten so far in this body of works. Now, what is that I want to say, which is a little bit more new? Well, part new, part old. I'm not entirely satisfied with this best case scenario. So I think that there are cases in which we need to assess the quality of our state and the usefulness in a broader situation. For instance, for this discrimination problem, we might not always be allowed to pick the best case problem for my state. We might want the state to be useful in different settings, even when we do not know a priori the exact specifics of this. So there might be maybe a library of possible black box, and we want to assess how useful our state is for discrimination in all of these different situations, not just in the problem for which my state is the best resource. Similarly, for the estimation case, it's a bit like preparing for an exam. So my input state is the preparation that the student does on their books. They don't know the exam questions when they study, right? So once they go through the exam, they're going through this unknown phase in which anything can happen. Then they open the envelope, they read what is the question of the exam. And then after that, of course, they will have to give their best possible answer given the preparation after they've learned the question. And then they will be graded. Now, if the examiner is particularly mean, instead of asking what the student is the most prepared for, they can ask the question for which the student is the least prepared. And so what's the opposite situation here to what I have shown so far is to consider these problems not in the best case scenario, but in the worst case scenario. And this is nice because it will really tell me how resilient is my state to this kind of problems, and not just its best case usefulness, but what it's guaranteed that my state will allow me to do, even in the most unfortunate situation. So we have to now reconsider the setting of convex resource theories, because these problems will be naturally described by non-convex resource theories. For example, suppose that I have my set of quantum states, and I have my state here, and I want to assess the usefulness of my state for different kinds of problems. For each kind of problem, there will be a set of states that is useless, right? Like before. So if I specify a certain discrimination or estimation problem, if I specify a certain Hamiltonian, a certain basis, now the incoherent states with respect to that basis will be free, and they form a convex set. But if I change my direction, then it will be a different basis. It will be a different set of free states, which will be considered useless as well. And if I change the setting again, then there will be a different subset of states, which is useless. So if I want to check how useful my state is against all of these possibilities, then I need to distinguish my state from the union of all the free sets corresponding to each subcase. So in this new resource theory, when I want to assess worst case scenarios, the overall set of free states is the union of lots of individual free states corresponding to convex subtheories for which I already know everything about. And so what can we say about these cases? First of all, why do we care? Well, there will be, for instance, in metrology, you might want to have some resource state which is able to pick up phases both with respect to, say, the z-axis and with respect to the y-axis. Okay, or if you want in magnetic sensing, you need to be able to sense magnetic fields in different directions. So these are versatile sensors for metrology. You don't need to know the direction a priori. They will be sensitive to both, to more than one axis. In thermodynamics as well. So thermodynamics is a resource theory where free states would be thermal equilibrium states at a given temperature with a given Hamiltonian. But you have some engines which operate between different thermal baths. So you need to be at non-equilibrium with respect to all of those in order to construct some resource engines. So again, the free states will be a union of thermal equilibrium states at different temperatures, which will form some non-convex resource theory. So there are physical examples. There are even some more natural ones, like Gaussian states. They are a non-convex set. And we know that Gaussian states are insufficient for many things in quantum information, continuous variable quantum information. So you want to be outside of that set. And they're a non-convex set. So it's interesting to look at non-convex resource theories more directly as well. So what did we do for phase estimation? Funnily enough, this problem, we have actually studied it 10 years ago in a different way and without thinking of it as an example of a non-convex resource theory. So let me just phrase it in a way that is relevant given the talk that I'm giving so far. So here, you don't know, at the moment of preparing your set, you don't know what will be the generator of your phase shift, right? It's blind to that respect. You just know the spectrum, but it can be, for instance, for a qubit, any direction in the Bloch sphere. So once the state goes through, some referee will announce what is the direction so that you can then perform your best possible measurement, and you can then quantify your precision in terms of quantum Fisher information. But if you want the worst case scenario, and you don't know a priori what is the generator, then for each possible directions, you would calculate the quantum Fisher information. And the worst case scenario is quantified by minimizing the quantum Fisher information over all the directions of the generator. Now, this problem is trivial, formulated this way, because in order to get anything different than 0, you would need an input state which has coherence in all possible directions, because you need to be able to pick up phase in all possible directions. This is impossible. It's impossible because every density matrix is diagonal in some basis. It's just a Hermitian operator. So if your worst case scenario is just the eigenbasis of the state, you will not have coherence, and your minimum quantum Fisher information will be 0 in that case. But this problem becomes non-trivial if you have some helper. So if your state is correlated with some passive ancilla, which does nothing, right? Does nothing. You prepare a bipartite state, just your probe goes through the unitary again, and then you do joint measurement, and then you reconstruct your statistics. And now you want to minimize the quantum Fisher information for this bipartite input state over all directions of the generator on this probe only. Yeah, the ancilla is totally passive. Now, this minimum is non-trivial. So this minimum is, we call it the interferometric power. It tells us how useful our state is for interferometric phase estimation in the worst case scenario in which you don't know the generator in the first place. So it's really a good figure of merit here. And what we found, seriously, 10 years ago, was that this quantity is 0 if and only if the state is in a very particular form, which is classical quantum state. So back in the day where quantum discord was popular, then what we found is that discord is really a resource for phase estimation in a worst case scenario, because just the states with 0 discord, they allow you to fail this, because they will be diagonal in some local basis. Every state which has discord, it means that locally they have coherence in all possible bases, just by the effect of being correlated quantumly with another ancilla. So whichever direction you pick, they will always give you a non-zero quantum Fisher information. And this interferometric power quantifies that precision in the worst case scenario. And we could show that it is a monotone and a candidate set of operations for a resource theory of discord, which would be an example of a non-convex resource theory, because this set of classical quantum states is non-convex. You mix two of them with different local bases, you generate some state with discord. So we have done this minimization 10 years ago, and now this is an example of just take the previous results from best to worst case scenario and identifying the non-convex resource responsible for guaranteeing a precision even in this situation. And we did experiments as well with NMR. That's old stuff, but it's good to revisit it. So having that in mind and conscious of time, we quickly are doing at the moment the discrete version of this. This is in collaboration with people in Japan and in Canada. And we can consider now the problem of channel discrimination, just with the same idea that we want our state to be able to successfully outperform free states, even when they are formed from the union of many different theories. So what we know? For each possible theory, we know that the maximum advantage is given by the robustness, but the worst case scenario would be minimizing this over all possible sets of channels that form the different sub-theories. So we will have the minimum over all J's, which correspond to this union here, of the maximum advantage in each set, which is the minimum of the robustness with respect to each convex set. And then it's very simple to show that this minimum of the robustness in each subset is actually equal to the robustness with respect to the combined free set. So you can equally, nobody I think has studied robustness for non-convex sets, but you can simply define robustness as before in terms of minimum weight until your state becomes free, even when the set of free states is now non-convex. And then this robustness will quantify the worst case advantage in channel discrimination with respect to all possible settings that are specified by the components of your theory. So that's a result that we have. And what we're trying to do now, we're trying to get something even more direct, saying if you don't have access to the individual components of your theory, can you always separate your state from whatever shape the free set has in terms of a discrimination problem? The answer is yes, but we need nonlinear witnesses for this problem. So before we said the whole mathematical core of the result was we can separate our state from the YOLK, the convex set, just by a hyperplane. That's a witness operator. All the rest followed. Here, if we need to do it with respect to a non-convex set, we need curved witnesses. Ideally, just 2 copies of my state is enough. We need the quadratic witness. We need something that defines a little bit of a curved boundary around my state, which can separate it from the rest. And here, we don't have to specify the subsets here. I don't know why I keep having this figure. We just need overall free state set. And then what we have at the moment is for every state which is non-free in an arbitrary resource theory, there always exists some discrimination problem, just one. We don't have to do all this minimization, just one problem for which my state has an advantage compared to anything in this non-convex free set, provided that we do the discrimination on D copies of the state, where this is the dimension. So we have this result, is the qualitative distinction. We don't have yet the quantitative thing, which connects the advantage here to some robustness measure, right? So this is something that is a work in progress. So I think I spoke a lot. So this is, if you have any ideas or follow-up works in this respect, feel free to approach me later. It's perhaps time to summarize. So today I gave you a little overview of some work we've been doing over a decade almost, yeah? So in a way or another, we've been looking at quantum resources and what we can do with them. And there's a lot of results for convex theories, up to the most general results, which show that every state that is not in a convex set of free states is useful for problems of channel discrimination or parameter estimation, in the best case sense, that you can always find one of those problems for which your state is the most advantageous compared to free states, and that advantage will be quantified by robustness or quantum feature information, depending on the setting. Some of these results can be generalized easily to non-convex theories with the idea of resilience and worst case approaches. By minimizing the figures of merit for the convex theories over all subconvex theories that form a non-convex theory, then you will still get some new figures of merit, which quantifies usefulness in these more general theories. We are trying to get some more direct results in this case that do not incorporate this worst case approach, although I'm personally quite keen on this worst case interpretation, because again, as I said, we were already doing this 10 years ago. It would be good to consider hybrid theories, which incorporate states, measurements, and combine them in this way, even when they are not just objects of the same class, but they are of different class, and look at combined usefulness of, say, states and gate sets. This might be helpful for quantum computing. And it would be nice to consider more physical examples that are relevant for what people really care about. So many of you maybe here, they can do experiments, and we can't just do, my mathematical approach would be take a state and find the problem. No, you have some problems in the lab. You have some things which actually are resources for you in the sense that they cost money. And we need to understand with what you have in place, what optimal use of your resources we can get in order to accomplish certain tasks. So we need to revert this approach as much as possible in order to bridge and close the gap which still remains between quantum resource theories from a fundamental mathematical interest and development of quantum technologies from an actual practical perspective. So back in the day when I published one of these papers, 2019, I wrote a poem about it. It's a sonnet. But now these days, there's AI which generates poems for us. So I don't know which is better, but I think in this battle of AI versus humans, I will leave the final slide on, which contains these two sonnets. One is mine, one is the AI one, but I'm not telling you which is which. So whatever it is, it's about the general result of channel discrimination and convex resource theory. So one, it was written by me. The other one, I just copied the abstract into ChatGPT and asked for a sonnet. So these are the two results. And thank you very much for your listening. I finished.
Yeah, very nice, Gerardo. Very clear talk. And just give us some time to go through these 2 poems, and then we can, we can go for questions. Yeah, to me, it's a guess, but the green one seems to have been written by you, or I don't know whether you would like to certify whether I'm right or wrong, but yeah, I leave it for you.
Yeah, the one on the left is mine, the one on the right is, but ChatGPT did quite well, knowing just the abstract of a PRL paper. Yeah, so I think it did quite well.
It's certainly, I mean, worth appreciating, but there is still some naturalness to the one on the left, as far as I'm concerned, but I don't know about the others. But anyway, both are very nice. And formally, thanks again for this very nice, wonderful talk. And now let us open it for questions and comments. So
I think Usha Devi has the hands up.
Usha, yeah, please. Usha, please go ahead.
Thank you. Very nice talk. I have a kind of very general question, like in quantum optics, you have a notion of P function, and then you go ahead with P function being negative or P function being singular as some kind of non-classicality. So I always wondered, do you have such a similar thing, at least in the case of SU2, say coherent states, and you talk about coherence theory. That is one question which I would like to you to comment.
Thank you.
So that is, it is like if P function is non-classical, you can generate entanglement when you pass it through a passive device like unitary beam splitter. In a similar way, do you have a notion of P function for your, say, a qubit, let us say, and then you pass it through some incoherent device, and then you do have entanglement or not, no entanglement if the P function, based on P function? This is just an academic question.
Yeah, it is a very good question, and I think I probably said it very quickly, but this result, which I have it in the slide here, that was exactly what you're saying. So
yes,
it's, I don't have it in terms of P. So first of all, there's a conflict of terminology because for optics, the Glauber, what we call coherent states, that would be the classical states, right? While here, in the case of quantum coherence as superposition theory, the incoherent states will be like the classical states. Okay, so when I talk about incoherent, think of, so in your scheme, think of this. Incoherent here means P function is positive and well-defined. Incoherent operation in quantum optics would be passive operations. And so if you have a positive P function with vacuum, passive operation, you don't get any entanglement. If you have negative P function, so in your case, say squeezing, Fock state, and you couple with the vacuum through passive operation, then you get entanglement. So we got exactly the same result here for all discrete variables. We don't have to go through the P function, but we characterize classical as being diagonal in a reference basis, and non-classical as having some off-diagonal elements. If we do that, and then of course we will have that the incoherent operation, so the free operations will be the equivalent of your passive operations. So this will be operations that are say, that are unable to create off-diagonal elements in the discrete variable case, then we get the same result. So actually in this paper, at some point we say, this is very much inspired by the result in quantum optics, for which non-classicality gets converted to entanglement or beam split, where non-classicality is defined in terms of P function, as you say. So yes, we have, this is the general direct counterpart of that in finite dimension.
Yeah, thank you. I understood this, but it's kind of a wish that we do have a P function in SU2 coherent state language also. So it is atomic coherent state language also. It was with the kind of academic spirit that I'm asking, is there an analog of P function? Not in this way. This I understand.
Ah, okay, sorry. Oh, yeah.
There is
There
an
can be.
analog.
Yeah, there can be. I know that there are definitely discrete Wigner functions and many things, but it's a good question. I am not aware whether results like this were interpreted in terms of some discrete P function. Certainly, for instance, we can do it for spin coherent states versus spin squeeze. That's okay.
Yeah.
Whether I can associate measures of coherence with some discrete distribution, impossibly true. I'm not aware. What I know is that some people were extending coherence theory to continuous variables just by starting from the P function, but then discretizing in a sense. So I have to check what they've done. These are people in Korea. So it's possible. It's definitely possible. Thanks.
Thank you.
Okay, other questions? So you can either raise your hand or write something in the chat box. Let's see. Anybody?
In the meanwhile, I will ask a small question if the chair permits.
Yeah, please
this
go
is
ahead.
about your identical states, identical systems that you mentioned. So I wondered if you used bosons or fermions, would that matter in your PRX paper that you mentioned about coherence with identical system, entangled identical systems?
No, in that paper, we did it both for bosons and fermions. Of course, there's just one parameter that defines the symmetry of the wave function. And then we had some results later on, which were related to, that's a different paper, were related to the paradox of mixing gases. And this changes a little bit between bosons and fermions. But that in that paper, we had for both.
Okay. Okay, thank you.
Thank you.
Yeah, so actually, I mean, taking Usha's question forward, so as far as I understand, there's a little bit of controversy regarding entanglement in identical systems. So something which arises just due to symmetrization or asymmetrization. So do you consider it as a resource or resources beyond that? I mean, what is the take on it?
Yeah, so so many ways of resolving this. So there's some ways which it depends whether you put labels or not. Other ways of resolving this is you just don't do entanglement at the particle level, but you consider mode entanglement only. So what we did is we defined the resource theory at the particle level. And so we defined particle separable states corresponding to ones that, so they will not have any additional entanglement on top of what is, as you say, just given by the symmetrization or anti-symmetrization. So that is not, the one coming just from symmetrization, anti-symmetrization is not a resource. But there is a way of formally defining particle separability versus particle entanglement in such a way that this will be in a similar scheme to this one on the screen, will be mapped into useful mode entanglement. So we consider particle entangled states are those that can be converted by means of suitable particle-free operations into accessible mode entanglement. So the ones that you say they would not be any useful resource if it's just formally entanglement coming from symmetrization.
Yeah, thanks. There is one more slightly sort of, you may call it vague question or general question. So most of your talk was related to a resource theory of states, although you did at times mention about resource theory of operations. Now, if we look into the latter category, for example, there are operations like, say, for instance, non-Markovianity. So has the literature progressed as far as considering, say, your worst case scenarios in that respect or things like that? Or,
as far as I know, no.
Okay.
But I think non-Markovianity is a very natural setting because non-Markovianity is non-convex by itself already. So
Yeah.
I think that's a very good playground for exploring this. So if you have students and if you want to work on that, and if you want to work with me on that, I'm happy to do so.
Thank you. Yeah, thank you. So that seems to be quite open and interesting. Yes, yes.
Yeah, as far as I know, yeah.
Thanks. Yeah. So now there is another chat. Okay, comment from Usha again. Yeah, in the chat box. So can you read it or?
Oh yeah,
read
I
it
can
out?
see it. Yeah,
Yeah.
about connection between phase discrimination with quantum random access code. That's a good question. I'm not very familiar with this actually. So we would have to see. So what I don't know. You can tell me more about it. Yeah. So I've read that there's this quantum random access code, but I don't know the connection to discrimination.
Because I thought that if you send it through sub-channels, it is like preparation of a quantum state and sending it to Bob, let us say, and Bob does a measurement MK, and then there is always an advantage in such average success probability is the
I see now.
QRAC,
Yes,
basically.
totally. Yes.
So now this is similar. Then in QRAC also you would use this kind of robustness of coherence kind of measures in QRAC. I don't think, I haven't seen such a thing being done. So I wanted you to.
Yeah, let's look at it. Yeah, definitely. I mean, when we first thought of this phase discrimination, we were thinking a little bit of communication as well, because it's like encrypt. Suppose each setting is like you're encrypting in a certain thing, and Bob has to do a little bit of decrypting. So it was some basic primitive for communication, and then of course you need coherence in order to do it better. Otherwise, you just get something scrambled. So would be good to give it more meaningful interpretation in a concrete setting, rather than one that we constructed just to prove a theorem, right?
Right.
Yeah, would be good. Thanks.
Okay, so I don't see any other questions or comments. So if there are none, so let's thank Gerardo once again for the very beautiful talk and for sparing his time, and we look forward to further interactions with him. So thank you so much once again. Thanks.
Thank you very much.
Thanks.
Thank you.